As he co-authored more than 350 peer-reviewed conference and journal papers with 18 Best Paper Awards, 2 books, and 1 patent. He is a member of the editorial board of IEEE Communication Surveys and Tutorials, IEEE Communication Letters, Springer Photonic Network Communication, and elsewhere optical switching and networking. He is a member of the technical program committee for various networking conferences such as Infocom, OFC, ICC, and Globecom. He acted as technical program chair of ONDM 2016 and DRCN 2017 and DRCN 2019 conferences. He has participated in several EU R&D projects, among others FP7 Combo, S2020, Metro Hall, and Cost Action, RECO DIS, as well as in several projects in USA, Canada, and Italy. So now this session is over to you, Professor Massimo. Yes.
Thank you very much, Amit, for your introduction. Welcome everybody. I'm happy to be here to share a little bit of my teaching on protection in optical networks, and hopefully we'll have time at the end of the lecture also to discuss a bit of research topics. I have a lot of slides. I'm not necessarily feeling the need to cover all of them. As long as you have questions, you can interrupt me anytime via the chat or even taking the voice and ask me questions. I guess we are all professors here, so we know how important are questions to make teaching easier. So feel free to ask questions at any time. So the main topic will be protection in optical networks. I'm going to organize the lecture this way. I'll start with some introductory concept just to be sure that some terminology and some understanding of what it is an optical network is common, is agreed among us. So not really talking about optical protection at the beginning of the lecture. And then I start with the protection at the optical layer. There are some very well established mechanisms for protection at the optical layer that go under the name of dedicated path protection, shared path protection, link protection. These are the main families, the main approaches for protection at the optical layer. And I'll try to discuss a little bit pros and cons of these approaches. But with current evolution of optical networks, is becoming more and more important to look also at the problems that arise when protection is performed at different layers of the network. Okay, so when there is protection at the optical layer, as well as there are protection in the higher layers, for example, in the IP or in the MPLS layer. This kind of situation makes emerging some other issues, which I summarize here as multi-layer protection issues. And if we're going to have time, I will also be happy to mention some of the research topics that I'm currently studying in terms of optical protection in optical networks. This has been always a research topic of mine. I did my PhD at the beginning of year 2000 on this topic, on protection in optical networks, and just to make a consideration, like off-topic consideration, I was one of the guest editors for IEEE Transactions on Network and Service Management on reliability in networking, and we got a very large amount of papers submitted, which really makes the point that reliability in networks in general, in telecommunication network, is an healthy topic, is a timely topic. Okay, so I know that during the school that you're attending, during this workshop that you're attending, most of your attention is on access networks. Very quickly, that the telecommunication network is typically conventionally divided in 3 domains. there is the access domain, which is basically long, very few kilometers, and it's typically based on tree-based topologies and allow users to connect with the first point of presence of the network operator. And I know that this is most of the emphasis of your workshop. Then the information that is collected by the users to the network operator is typically further aggregated in another segment, which is called metro, which spans few tens of kilometers, and it is typically ring-based or interconnected ring-based. And then the information goes to the national or even continental network that we used to call core or long-haul networks that can span hundreds, if not thousands of kilometers, and is typically mesh-based, right? It's typically having a topology which is mesh-based. So my attention is going to be mostly on the long haul, on core networks. But even, just by looking at this very preliminary and simplified structure of the telecommunication network, there is already a message in terms of reliability, right? Because while here we have trees, which basically do not have chance of reliability unless you do some redundant trees, but we're not going to get into that topic. What happens in metro is that you really start adding to your network a first degree of reliability, in the sense that when you use a ring, if you have a failure on one link of the ring, you at least have the possibility of going on the other side of the ring. Things that was not happening in the tree, right? In the tree, whichever link is failed, you basically disconnect some of the users. So the ring network is the first network topology that allows a certain degree of reliability. In core networks, people are using mesh topologies, and the mesh topologies are indeed motivated, among other reasons, also by reliability, because if you think about in a mesh network, if you have a failure on a link like this link, you're not anymore forced to travel with the secondary path all over the entire edge of the network, but you can somehow shortcut. You can shortcut your backup path on a shorter path. So the utilization itself of a mesh network for large core networks is due, of a mesh topology, is due indeed to the fact that reliability, that protection can be enforced with lower cost. Anyway, long story short, we're going to concentrate on the core network in this lecture. And we know that optics is present in all the segments, on all the three segments of the network, in access typically through the PON technology, in metro through gigabit Ethernet or OTN, SDH technologies. We're going to mostly assume a technology for the core in this lecture, where we have optical cross connects co-located with routers. And so we will see there is possibility to both switch light at the physical layer with the OXC, with the optical cross connect, or switch packets in the electronic domain through the core router. And we will see how these two things interact. So I'm not going to spend much time here. We all know that using fiber optics has a reason. I mean, that there are very strong technical motivations for which we use. There is a problem with my voice. Somebody says in the chat that my voice is not available.
Your voice is very clear. There might be some connection.
Maybe Rajesh maybe it's some problem by specifically Rajesh. I hope everybody else except Rajesh can hear me. Please let me know if the problem is more spread. Okay, so I was saying, we somehow all agree on the fact that transmitting bits from A to B, from Now, if we're talking about point-to-point transmission between A to B, then there is no discussion that fiber transmission is the way to go. Okay, just quickly making a couple of examples. Here I'm plotting the spectrum of the fiber as a function of the frequency. As you can see, the spectrum of the fiber is indeed in the neighborhood of 10 to the 15, in the neighborhood of petahertz, while the spectrum of all the other transmission technologies is in the order of megahertz, hundreds of megahertz, maybe gigahertz, but still we have several orders of magnitude before getting to the spectrum of the optical. Okay, so when it comes to passing bandwidth, there is no discussion that we are using the fiber. When it comes similarly to attenuation, again, there is no discussion that we are using fibers. Typically, in the window of utilization, in the transmission window of an optical fiber, which is typically around 1500 nanometers, the attenuation is 0.2 dB per kilometer. And this attenuation is way lower than the attenuation in copper, just to make an example, which is in the order of 5 to 15 dB per kilometer, or even much more than that. Okay, so when it comes to transmission, no discussion that we want to go in optics. But the other point, which is interesting to see here, is the third point that I had in the last point, sorry, that I had in my slide, which is optical switching. So is it optics also useful for switching? And here I'd like to spend 1 minute at the beginning of the lecture, okay, with an example. So from a networking point of view, the application of optical technologies, when it comes to using the large bandwidth of the network in an optical network, we basically use WDM, right? We divide the enormous spectrum, the petahertz spectrum of the fiber through wavelength division multiplexing, which basically means that we take the spectrum of the fiber, we divide the spectrum of the fiber in different channels, and we multiplex the different channels over the fiber. To be more specific, usually the transmission system in practice are bidirectional, so you have one fiber WDM based in one direction and one fiber WDM based in the other direction. But what is interesting is to see how optics is currently being used, especially also in the switching domain, not just in the transmission domain, A to B, but also in the switching domain, the moment in which you have to decide how to route information into the network. So let me just make an example. Now let's assume this is San Francisco, and this is Los Angeles, and this is San Diego. Okay, and we are transmitting some information between San Francisco and San Diego. Okay, so we have, let's say, 2 connections, each of them at 100 gigabit per second between San Francisco and San Diego. So traditionally, the information was exchanged through elements called switched through elements in the electronic domain, like IP routers. Okay, so forget about this element here. We only have IP routers. So what was happening traditionally was that the 200 gigabit per second information was sent by San Francisco to LA. In LA, the information was translated from the optical domain of the transmission to the electronic domain of the switching. And then it was translated back again in an operation which is called typically OEO, optical electronic optical conversion. And it was going to San Diego, right? That was let's say, the old mode of operation, the traditional mode of operation. That meant that even though the information was destined to San Diego, in LA, we were having 200 gigabits per second of traffic elaborated with all the cost and energy consumption that that involves. Recently, and with recently I mean the last 15 to 20 years, what happened in terms of network architecture is that in the intermediate nodes, network operators have started placing not only routers, but also optical cross-connects, co-locating optical cross-connects with routers. Why they were doing that is possibly shown in the animation that I have here. Now, if I have two requests at 100 gigabit per second, for example, this request and this request, these two between, again, San Francisco and San Diego, and let's say Reno and San Diego, when the information gets in LA, we do not really need to pass through the router. We just stay in the optical domain. We just stay in the OXC, which has a cost and a energy consumption which is orders of magnitude lower than the router. And so also the switching in the network, in the optical domain, the wavelength switching has a strong impact on the cost minimization of the network. So from now on, whatever I will discuss in terms of optical protection is based on the idea that in the intermediate nodes of your path, you can indeed use some optical cross connect, some OXC, in order to avoid router elaboration of the signal, electronic elaboration of the signal. Again, if you have any doubts or curiosity about what I'm saying, just interrupt me, no problem. I think it's more important clarity than covering all the material. Okay, so in the context of optical networks, we want to concentrate our attention in this class on protection. But again, I need to introduce some preliminary concept in the unprotected case in order to show the importance of protection later. So when we talk about problems of resource allocation in optical networks, is it important to divide two high-level concepts, the logical topology versus the physical topology? So when I say logical topology, I have in mind typically a customer of the network operator. And the example that I like to do is typically a bank, okay, which can be like a large customer of a network operator. The bank has electronic point of presence. So these are most of the time IP routers, okay, typically located in different cities. And the logical topology for the customer is really the set of connection requests among the various routers that the bank requires and that the bank asks to the network operator. Okay, so the logical topology, it's called logical in the sense that is the network topology perceived by the customer, and it's a network topology that it's independent, somehow doesn't matter about how the connections are actually routed over the physical link. On the other hand, so on one side we have the customer, on the other side we have the network operator. So on the other side, from the perspective of the network operator, we have what we call the physical topology. Right? The physical topology is formed by fibers, so optical equipment, fibers, optical cross connects, transmitters, receivers, etc. etc. Okay? So the objective of the network operator is really to receive the request from the bank, from the logical topology, and provide a mapping of the request coming from the customer over its physical topology. Little parenthesis before I move on. little parenthesis before I move on. The nodes in the optical cross-connect nodes can be of 3 types. And let's concentrate only on these 2 types. Can be OEO nodes or basically OOO nodes. In the OEO nodes, the information arrives in optical. It's again translated in electrical and then again translated in optical, like you can see in this example. This kind of switches were popular till a few years ago. On the other hand, the current optical cross connects are node architectures in which the information can bypass directly the optical. Okay, doesn't really probably matter too much for the rest of the lecture, but we still have in the field both OEO optical cross connect and OOO optical cross connect. This is obviously the more modern architecture. Anyway, going back to the problem that we're trying to solve, we have a logical topology on one side, we have a physical topology on the other side. This is the customer view. This is the network operator view. What the network operator has to do is to take each of the requests, for example, this request here, CR3, and for this request, it has to define over its physical topology, it has to define a routing. In this case, for example, CR3 is routed this way. It could have been routed this way, right? So you need to find the routing, and you need to find also an assignment of a wavelength, which in this example, the assignment of the wavelength is represented by the color, in this case, the green color. This problem that we are solving is called routing and wavelength assignment. If we add also the dimension of defining how many fibers you need on a certain link, you might have more than one fiber, then you call it a routing fiber and wavelength assignment. Okay? So we want to solve this problem, of course, in an unprotected manner, which means by providing only one path in the physical network for each request in the logical network, or we want to solve this problem considering protection dimension, so considering redundancy of. For those of you who might be less familiar with these concepts, I try to make an example which is probably more visual. Now imagine this is AT&T. Okay, this is the logical topology of AT&T. And on the other hand, this is the logical topology that Bank of America wants to support. Okay, Bank of America would like to have a connectivity between Utah, Illinois, California, Texas, and so on offices. Okay. When I say that we perform a mapping of the logical topology over the physical topology, which is basically a routing and wavelength allocation, I really mean what I show in this example, right? For example, if I need to connect Colorado with Washington is this link, then I need to find the routing into the network, like this one, and I need to find the color to associate to this routing, a wavelength associated to this routing. If I do the same for all the links of this logical topology, so I keep going, adding all the links of the logical topology over the physical network, you will see that the mapping of the ring doesn't really look like a ring. No, I'm starting from Utah, I go to Illinois, then I go to California, then I go to Texas, Washington, Colorado, New Jersey, Pennsylvania, and then I go back to Utah. It is a ring. So if you start from a node, you're going to go back to that node, but it's mapped over the physical topology. So the problem that we solve is this one. Given the logical, the physical topology, So the requests and the network to serve those requests. We want to route the light paths, assign the wavelength, and possibly decide the number of fibers, minimizing some cost metric, which can be the cost of fiber, the cost of wavelengths, etc. Is this a complex problem? Yes, it is a very complex problem. If we solve it only in its RWA version, is MP complete. If we solve it also with fiber assignment, it's indeed MPR. So it's a very complex problem. The problem when you deal with these problems in practice becomes way more complex indeed. Okay, so for now we have considered somehow 3 dimensions of complexity: routing, wavelength, and fiber assignment. When you really deal with these problems in practice, you might consider that connections come and go, so there is time to be considered, physical layer impairments to be considered, application requirements like latency to be considered. Each connection can be a different rate, so there are mixed rates that coexist into the network. Protection, which is what we're going to discuss from now on in the remaining hour. Aggregation of multiple requests in the capacity, energy minimization, different vendors interoperability, different domains that constrains the routing, cost, etc., etc. Okay, so whatever I'm saying is intended to say, obviously, the way I'm showing the problem is quite simplified. In practice, there are so many dimensions to consider. Anyway, let's start talking about protection. It's been almost half an hour now. So now that we have a little bit defined the context in which we are moving, let's talk about what are the techniques to ensure protection. And let's start with some motivations, okay? So why protection, especially in core networks, is universally considered as a main design driver of the network. The reason is quite intuitive. In optical networks, the amount of bandwidth carried by each link is just enormous. It's just huge, okay? Typical example. I guess somebody has gone not in mute and there was some echo. If we consider a typical cable in a network, the cable can be equipped with up to 200 fibers. Each fiber can be nowadays, it is a bit on the higher side, but it's reasonable, up to 160 wavelengths per fiber. If we consider that each wavelength goes at 10 gigabit per second, which is not even what happens today, because today we can go easily to 100 gigabit per second. The overall amount of information is just huge, right? It's 320 terabit per second in a single cable. So it is obvious that we cannot really afford as operators to stop 320 terabit per second and not having a secondary plan in action in order to avoid this situation. Just to make some example, 320 terabit per second means 5 billion phone calls at the same time, or 60,000 full CDs being exchanged per second. Is there a question? So, conclusion, a single cable cut can determine a dramatic amount of lost traffic. So we need to have solutions in place such that when a fiber is cut, you have alternate solutions to carry your traffic. Not only you need to have a secondary path, not only you have to have a backup plan when there is a failure, but the backup plan must be reacting, must be available very quickly. And when I say very quickly, I'm talking about milliseconds. Let's again make a very simple calculation. if I have a 1 millisecond outage, 1 millisecond, okay, not 1 hour, 1 millisecond, in a fiber which carries 100 wavelengths, each at 100 gig, that means basically that I'm already losing the information contained in a CD-ROM. Okay, so now consider the same thing when it's 1 second, 2 seconds, 1 hour. Obviously, the speed at which you solve the problem is extremely important. Solving the problem in 1 millisecond, or solving the problem in 10 milliseconds, or 100 milliseconds, for an operator is very different. Okay, so also what we call the protection switching time, the speed by which you go to the secondary path is extreme. Further motivation of what I'm trying to say, how often a network is broken. So let's again make simple calculations. This is a US network. An operator in US has identified an average amount of failures per year equal to 2 failures every 1,000 kilometers every year. Okay, 2 failures every 1,000 kilometers of fiber per year. Since a North American network is easily getting to 100,000 kilometers, that means that there are 200 failures per year. 200 failures per year. And since in order to fix a failure in a network, you need to send a repair crew, to fix the fiber cut and so on, and it takes at least 1 day, it means that on average, 200 days of your year are going to be affected by failures, which means basically most of the time the network is broken. It's not that the network is broken sometime. The network is most of the time broken, if not always broken. So we need to design the network in such a way that the failures are accounted during the design. Let me tell you something additional, actually. I was talking with some friends working in Nokia who had a network in India. And they said that in that network in India, long distance network in India, they indeed experience easily 3-4 failures at the same time. Okay, so it's again, protection is not something you do just in case. It's the normal operation of the network. You need to have protection. And the reasons why you need protection are so diverse, right? Typically, it's dig ups or agricultural situations in which there is some plowing and they just cut the fiber. But there are some very funny reasons for which the network can be broken. And I invite you to go check the sharks, okay, in YouTube, the sharks biting the fiber cables and breaking the fiber cables. That's one of the thousands of reasons why you can indeed have a fiber cut internet. So on one side, we have the customer, which requires for some quality of service, availability. On the other side, we have the operator, which doesn't want to spend too much money. It turns out that protection is not performed only in one manner. There are tens of ways of performing protection in order to find the right balance between what the customer wants and what the operator can provide. Typically, the customers ask for a specific metric of quality in terms of protection, which is called availability. If you look in the internet for service level agreements of operators, you see that service level agreements typically refer to availability, which is the percentage of time in which the network is available for them. Okay, so this is just one example of megapath. If you want to look it up, is freely available. Okay. So yeah, the main matrix to evaluate the quality of the protection provided by the operator is really the network availability, which can be easily calculated as 1 minus the mean time to repair divided by the mean time between failure. So I'm not now getting too much into the details of the meaning of mean time to repair, mean time between failure. I'm somehow assuming that you know these things, but you can easily look it up online. Just to give an idea of how the availability is typically negotiated, stipulated with customers, people usually call about a number of nines. They say my service is 1 9, 90% availability, 2 nines, 99% availability, 3 nines, etc., etc. That basically refer or can be represented in terms of the average unavailable period in 1 year. So if I have 3 nines, it means that my customer will experience at most 9 hours, 4 nines, 50 minutes, 5 nines, and 5 nines is really what typically operators want, is 5 minutes per year of unavailability. And in order to have 5 minutes per year of unavailability, you really need strong protection techniques. So typically it's availability, as I already said, as metric to define the quality of protection. Resource occupation, the customer doesn't want to utilize too much capacity in its network, and protection switching time, how fast you go to the secondary. So there are two ways of dealing with failures in optical networks. Either you go with protection or you go with restoration. What does it mean, protection and restoration? Let me quickly clarify this. Protection is a proactive technique. Protection means in the design phase of the network, you pre-allocate for your connection one working path and a secondary path before the failure occurs. Okay, so your network is designed in order to have at least 2 paths. In this case, you're going to have guaranteed recovery. If you have a failure, you immediately have a secondary path. Very short recovery time. You have a failure, you immediately go to the second path. On the other hand, no, the dark side is that you occupy double of the capacity, right? Because you pre-allocate the capacity. Restoration is instead a reactive approach. You just provide one path for your connections, and then if there is a failure, you look for another path. This is indeed good for some reasons, because if, for example, if you have 2 failures and the 2 failures in protection affect the first and the second path, you don't have a third path. While in restoration, as long as there is a path, you're going to find it. So there's some flexibility, which is actually desirable in restoration. On the other hand, typically restoration requires a long recovery time because you need to find the second path and you need to deploy a second path. And this might take several minutes, seconds, even hours, and it might not be acceptable for it. So that's the reason mostly why we concentrate on protection, and specifically, as I said before, on protection in mesh networks. The most obvious way of providing protection in an optical network is dedicated path protection. Dedicated path protection means that instead of providing, as I show in this example, one path between the source and the destination, you provide 2 paths. Okay? So instead of providing only the red path, you provide also the blue path. Obviously, the primary path and the secondary path must be, as people say, link disjoint. So they should not share any link. Otherwise, if there is a failure on a link which is common, both the paths will go down, right? So typically, the additional capacity that you need for this network is, well, I say 50% additional capacity, but I mean 100% additional capacity. Couple of observations regarding dedicated path protection. Okay, so let's assume this case here. We have connection from basically Los Angeles and New York. We have a primary path and we have a secondary path indicated by the dotted line. Okay. The distance in such a network is pretty large. Okay, summing the two parts, we are talking about 10,000 kilometers. Now, as I said before, when you evaluate a protection technique, it's not just about the capacity that you use. In this case, there's a lot of capacity used because you use twice the capacity. But it's also about the protection switching time. How long does it take to go on the secondary path? How long does it take to get the service back again? And let's see what is, for example, the protection switching time in this example. Assuming we have a failure between node 16 and node 21. Okay. Then what happens is that node 16 has, first of all, to detect the failure occurrence. So the red period of time, 20 milliseconds. After it has detected the failure, the information has to travel back to the destination, which is these other 20 milliseconds. It's called notification. You need to go back to the source and tell that there was a failure. And then there is what people call the recovery. So the time needed for the information to be switched on the secondary path and reach the destination, which is this other animation here, which leads the amount of kilometers traveled to be pretty large. You need to go from 16 to 3 and then to 3 again to 21. So even though dedicated protection seems to be almost instantaneous, it is not. It requires to have, in this case, about 70 milliseconds of delay before you get the information. Okay? There is indeed a way to solve this problem, to solve the problem of high protection or large protection switching time. And it's the case of what we call 1+1 protection. In 1+1 protection, we do not just have a primary path and a backup path, but we send the information at the same time on the primary and on the backup path. In this way, if there is a failure, you don't have any way, you don't have any way a penalty on the protection switching time, because you are at the same time sending the information on both directions. So basically your protection switching time is about 0. But it's 1+1. You are sending the information on both sides. Another way of implementing path protection or dedicated path protection is what people call the one-to-one protection. Okay? In the one-to-one protection, you send live traffic on the primary, and on the backup path, you don't send traffic unless there is a failure, which is what I've shown in the previous example. Obviously, this allows to reuse this capacity if needed, for example, for preemptible traffic or low priority, as I call it, traffic. But it requires a higher protection switching time. What I'm trying to say here, basically, is that protection techniques can be implemented in different ways with different trade-offs between the protection switching time and the capacity utilization. And this example of dedicated path protection is quite exemplificative.
So there is one question from my side.
Sure.
Yes, in this 1+1 protection, are we transmitting the same information from both the paths?
It's exactly the same information.
Okay.
And in order to show that 1+1 is much more costly than 1-to-1, even though they are both dedicated path protection, there's another aspect to be considered. In 1+1, you need two lasers at the same time. So you have to pay for two lasers. While in one-to-one, you can have one laser and then just switch on the backup path. So the cost is very different between the two.
Okay. Yeah. Thank you.
Thank you for the question. And then there is another version of this protection, which is M2N, dedicated protection. In M2N, the idea is that you can have M primary path and N backup paths, which are dedicated to the M primary paths, and somehow you save some capacity, even though you have somehow a dedicated protection. So, in conclusion, you have different ways of providing protection, from 1+1, which is the highest level of protection, to 1-to-1, to M2N. Obviously, availability decreases, but also cost decreases. And instead, protection switching time also increases the more you go in this direction, okay? Okay, another way of dealing with the high cost of dedicated path protection is to use what people call shared path protection. In shared path protection, the concept is this one. I'll use an example to show it. Imagine you have two primary paths, which are the blue paths here. And for these two primary paths, you have corresponding backup paths, the red paths here. So the idea of shared protection is that the capacity which is used on this intermediate link can be reserved only once instead of being reserved twice, because you start with the assumption that there are no two simultaneous failures. Either there is this failure or this failure. So either the capacity on this link will be used by this path or by this path, okay? So the rule is you can share the capacity for backup among working paths that are failure disjoint. So in this case, for example, the two working paths do not share any link, and so they are considered to be failure disjoint. Okay, so shared path protection is an evolution of dedicated path protection in which the backup capacity can be shared among link disjoint working paths. So this obviously allows us to decrease the cost. Okay, so the cost of shared path protection goes down. What goes up is the protection switching time. The protection switching time goes up because, first of all, protection in shared path protection is reactive. Okay, there's a failure. After the failure, I send the information to the backup. And when I go on the backup path, I also have to reorganize, let's say reconfigure the intermediate OXCs. So these OXCs cannot be, people say, pre-cross-connected. They must be cross-connected after the failure, and this takes time. So the protection switching time goes up. The availability obviously goes down, because now there is a larger set of double failures that cannot be recovered. Okay, so for example, this double failure cannot be recovered. If I have this double failure, only one of the two connections will be able to get service. In dedicated protection, this double failure that I'm indicating here would be solvable. In shared protection, it is not. Any question on shared protection? So just to make an example of how the capacity is assigned in shared protection, see here, I have three working paths in blue, 5, 4, 3, is the capacity, are the capacities of these working paths. And the backup paths are the lines in dotted red. If I use dedicated path protection, how much capacity I need on this link? I need 5 units to protect this guy, 4 units to protect this guy, and 3 units to protect this guy. So 3 plus 4 plus 5, 12. In share protection, I just need to take the maximum among the 3, because the 3 blue connections are linked disjoint. Okay, they don't fail together. So I'm gonna put on this path only 5 units of capacity. If the working paths that I'm protecting are not linked disjoint, for example, now the blue path shares a link with this other blue path, then the capacity that I need here is the maximum capacity needed on a link where I have the working paths. So in this case, this link requires 7 units of capacity. So here I will need 7 units of capacity. Okay. So the capacity that I need to deploy is always the maximum capacity that can fail at the same time. The maximum capacity that can fail at the same time is, in this case, 7. Okay. Indeed, making this calculation is not easy, and there is a system to make this calculation, which is called the link vector. Okay, this link vector is defined in this IETF recommendation, RSVPT extensions for shared mesh restoration and transport. Let's see, what time is it? Yeah, let's I think this is interesting. So let's see how this link vector works, okay? So a link vector is defined, let's not waste too much time on the math, okay? Is defined as a vector which has as many entries as the number of links into the network, okay? So for example, the link vector of this link will have 1, 2, 3, 4, 5, 6 inputs, okay? So the link vector is a vector associated to each link which has as many input as the number of links into the network. In this case, I could even put 7, the link itself. Now let's see an example of practically using the link vector to decide the capacity for share protection. And let's consider the link vector of link E5, okay? How the link vector of link E5 evolves in time. Let me tell again, the link vector of link E5 is the data structure that allows you to know how much capacity for share protection you need on link E5, okay? So at the beginning of time, we have no connections into the network, so the link vector is all zeros, okay? Each element of the link vector says how much backup capacity I need on link, for example, E1, when link E5 fails. Okay, this is the information of the link vector. So let's see it in action. For example, if I route connection A on this working path, link E2 and link E5, and with this backup path, E7, E5, E4, then the link vector says, on link E5, I need 1 unit of capacity when link E2 fails, 1 unit of capacity when link E3 fails, and 1 unit of, and that's it. That's it. These are the only 2 situations in which I need capacity on link. How much capacity I need? 1. If I have another connection, B, okay, that is protected this way, what happens to the link vector? Well, the link vector will tell, now I need 1 unit of capacity for link E1, 2 units of capacity, because on link E2 I have both B and A connections, 2 units of capacity for link E2, and 1 unit of capacity for link E3. So overall, the capacity that I need for share protection is always the maximum among all these values. That's the trick of the link vector. The link vector allows you to know how much capacity you need on link E5 when all the other links fail. And the amount of capacity that you need is the maximum among all these values. Okay? I know I went quite fast. I usually take a lot of time to express this kind of examples. But the main message is there are automated ways to calculate the amount of capacity that you need for share protection. And this information is carried, for those of you who are more familiar, by OSPF-TE. They are carried by the traffic engineering version of OSPF. In conclusion, dedicated protection requires more capacity, that's bad, minus, but it has higher availability, it is simpler to calculate, and is faster. Share protection requires less resources, that's good, but it has lower availability, higher complexity, and longer recovery times. Link protection. In link protection, we change the perspective. In link protection, we say we do no more protect end-to-end, so a connection between the source to the destination with a backup path. No more. What we do is we take one connection and we protect separately each link of that connection. So in this case, we will have a backup path for the first link, a backup path for the second link, and the backup path for the third link. Okay? So now the entity which gets protected is the link, is no more the path. It used to be the path, now it's the link. And this can be, again, performed in a dedicated fashion or in a shared fashion. We can have dedicated link protection or shared protection. Further observation, when we do link protection in an optical network, we can either decide on a link that we protect the entire fiber with a secondary fiber route, or we can decide that each of the wavelengths over this fiber are protected separately. As you can see, in this case, the 3 wavelengths with the 3 different colors are protected on 3 different paths. We say that we perform fiber level link protection versus wavelength level link. In conclusion, we have 4 approaches: dedicated link protection, dedicated path protection, shared link protection, shared path protection. Conceptually, we have 4 approaches. If we compare the cost expressed as number of fibers that I need to support a certain traffic matrix, I'm doing this on a US network as an example. Let's concentrate on this case here, the case where the number of wavelengths per fiber is equal to 8. I think this case is very easy to visualize, because the dotted line that is the unprotected case is about 100 fibers. So it's a good baseline. Okay? So this is the amount of fibers that I need in the unprotected case. 100. How much fiber I need in the dedicated link protection case? 400 fibers. So I have basically a 400% additional capacity. Or no, better said, sorry, a 300% additional capacity, right? This is how much more I pay. This is basically unacceptable unless you really have a very rich customer. This other case, the green, is the dedicated path protection. In dedicated path protection, the value is about 220. So if this is dedicated link protection, in dedicated path protection, we have about 120% additional capacity for protection, which is reasonable because why is not 100% but is 120%? Because usually the second path is longer than the first path. So the second path is more costly than the first path. But still is high, no? You are doubling the capacity that you need. These other two values, which are more or less the same, are the shared cases, and they stay around 150. So for shared path protection and shared link protection, the amount of additional capacity is about 50%, which is more acceptable. Okay. Obviously, this is only one side of the coin. If you look at availability and protection switching time, the performance is the opposite. Dedicated link protection will be the best, and this will be the worst. But if you are looking at cost, obviously, this is the best. Questions? So, we have another half an hour. Let's start looking at what happens when you don't associate protection only to the optical layer, but you start considering that protection is something that is performed at different layers of the protocol stack. Okay, so in this second part of the lecture, we consider that we do not only have optical layer survivability, but also IP layer survivability and MPLS layer survivability. I will quickly talk about IP layer and MPLS layer survivability, but especially I will talk about how they interact when you have together the optical layer survivability and the IP MPLS layer survivability. We will see that the survivability, especially at MPLS layer, is very similar to the survivability of the optical layer. So you have dedicated, shared, link, path, it's the same concept. So probably most of you know that the protocol stack in a transport network can be very complicated, with several layers. Let's simplify and consider only IP over MPLS over optical. That's it. Okay, we don't consider a more complicated scenario. So we have routers and we have optical cross connects, 2 layers. That's it. Let me skip this. I think everybody knows IP and MPLS in short. So I'm skipping the description of IP and MPLS at high level. I'm assuming people know what is IP and what is MPLS, otherwise it takes too long. And let me go directly to this observation. Now, let us observe how protection is provided at layer 4 by TCP, at layer 3 by IP, at layer people say 2.5 MPLS, and at layer 1. We already know. We already discussed it at layer. So every layer somehow has its own availability and survivability protection approach, okay? In the TCP layer, it's really end-to-end, the story, because you know that there is a window, a sliding window mechanism in TCP, except for the 3-way handshake at the beginning. You send your data with a certain number associated with the bytes. and you only send the new bytes when you receive the acknowledge. Okay, so if everything goes fine, you send the data, you get the acknowledge, you send new data. At a certain point, if you don't get the acknowledge because the data is lost, what you do is you wait for a timeout and then you send again the data. So this is somehow protection, right? Because if the data doesn't acknowledge, then you resend the data. So first observation, there is a certain protection, a certain servability at the TCP level. Obviously, if you're using UDP, let me go quickly, that doesn't work, right? You know that in UDP, there is no acknowledge check. So in UDP, if you lose the data, you lose the data. So layer 4 has its own servability mechanisms. Layer 3 also has its own servability mechanisms. Let me not overly comment the writing. Let's just see an example. So in the IP layer, what happens is that if you have a failure, like this failure between E and D, automatically the link state advertisement of the routers, the OSPF messages of the routers, will advertise that this link is no more present into the network, right? So the link ED, sorry, the node E, which used to advertise, I have two neighbors, A and D, will start advertising that it only has one neighbor, E, right? AE. Link ED is no more advertised. This advertisement is then sent into the network, okay? So it's received by everybody. So node C will receive the advertisement of E, which is this one, the advertisement of A, which is this one, the advertisement of B, which is this one, the advertisement of D, which is this one. We'll write a list, the link state database, a list of links, and it will reproduce an image of the network thanks to the link state advertisement received, which is an updated vision of the network in which this link is no more present because it's broken. Over this network, which has been updated, removing the link ED, we can run Dijkstra, and we can update the routing table. So this iterative process, which starts when you have a failure, allows the routing tables to be readjusted, re-updated every time there is a failure. So in conclusion, IP by itself, even without protection at the optical layer, IP alone is able to solve the failures. The problem is that all this iteration, this mechanism, takes long. It might take several minutes, and an operator doesn't have so much time to wait before a failure is solved. MPLS does similar things to physical layer protection, to optical protection. We have protection and restoration, end-to-end path protection. Simply in MPLS, it's called global instead of it being called path, but it's the same thing. And it does link protection. Simply, instead of calling it link protection, MPLS people call it local recovery, but it's the same thing. Okay. So very quickly, in MPLS, you have the dedicated path protection. It's called global path protection. And you have also the recovery. So after the failure, you calculate the backup path, as you can see in this example. This is called global default restoration. Only observation I want to do, obviously, if you do restoration instead of protection, the backup path, which is this one, since it is calculated after the failure, can reuse some of the capacity of the working path. because it's calculated after the failure. And in fact, in protection, we have disjoint paths. In restoration, we do not necessarily have disjoint. Local protection in MPLS is also very similar to the link protection we discussed before. Imagine you have two paths. Imagine there is a failure. In what people call local protection of detour, they also call it fast reroute, if you ever heard about it. What happens is that each connection affected by the failure is protected separately. So we have a separate path for the blue line and for the green line. Instead, the other version of MPLS local protection, which is called facility backup, simply, when you calculate the backup path, is a single backup path for all the connections on the same link. So you see here you have two backup paths for the two connections. Here you have a single. Now that we had very quickly in 5 minutes understood that there is also protection at layer 3, MPLS IP protection, let's see how the protections interact. Okay, the layer 3 or layer 2 and layer 1 protection, the optical protection. So let's assume again we have the logical topology. Now it should be clear. No, the logical topology, this is my customer, this is the bank, and the physical topology, this is the network of the operator. And let's imagine that we want to protect a connection between logical node A, the router A, and the router C. If we do protection only in the optical layer, see what happens. If we do protection between A and C, we have a light path associated with the logical path AB, which is this one. A light path associated with this logical link, which is this one. And the protection, so this is how, let's say, somehow the packet is going to be routed. And the protection happens only at the, only at the physical layer, right? So for the light path, the working light path, we have a backup path in the physical layer. But there is no protection action going on at the logical layer. If instead we do protection only at the logical layer, in the logical layer we have a backup path, okay? Not in the physical. Well, there's always a backup path in the physical, but there is initially, since the beginning, a backup path in the logical layer. So you need to map both your working logical path and your backup logical path into the physical layer. So this is somehow the snapshot that you have. You have working and backup connection in the logical layer, which are mapped on working and backup connection in the physical layer. Still, we are considering protection in the optical layer and protection in the logical layer with no interaction. But indeed, these two protections can interact. Okay, let me skip pros and cons of protection in the optical layer and in the logical layer. You can check it. You can check it alone. I want to go also on the research topic, so I'm hurrying a little bit now. The idea is to combine the recovery in both the layers. So let's see this example. Okay, in this example, we have jointly the protection at the physical layer, which is this blue protection here, and the protection at the logical layer, which is this red path. Okay? Now to map the logical protection, I need this physical path. So see what happens now. In this moment in which you have protection at both layers, you need some form of coordination between the two layers. If you do not have coordination, the situation can get nasty. You can have what people call root flaps. Let me make an example, okay? There's a failure. Due to this failure, the cross-connect send a message which is called alarm information signal, AIS, to the routers, okay? Routers get this information, the information regarding the failure in the physical layer, and react. What does it mean that they react? Let me see if I can make the animation work properly. Apparently not. Okay, the routers react. As I said before, they send the link state advertisement to reconfigure the IP domain. And so the traffic is sent on the secondary path of the logical layer. But then, I know this is a bit tricky, but then if the physical layer protection kicks in, as you can see, then the flow goes on the backup path in the physical layer. I have to send again information that the problem has been solved. And so in the IP domain, what happens is called a route flap. So I was going on a route. For a few milliseconds, I go on the second route. As soon as the physical layer reacts, I go back on the first route. So I'm basically moving traffic from one route to another just for few milliseconds of time, which doesn't make sense. So people do what is called coordination between layers, okay? And in order to coordinate the protection at the different layers, they use the hold-off timer. What does it mean? I have a failure. I send the AIS, I send the information about the failure, but the routers, instead of immediately reacting, they wait. They wait for a time which is called hold off. This time is needed for this reason. If the physical layer succeeds in solving the problem, the router doesn't act, which is this case here, okay? The physical layer succeeds, and so the router doesn't act. Let me go. Exactly, they cancel the timer. If instead, let me see if I have the, no, I don't have the animation, unfortunately. Anyway, if instead, for example, I have a failure here, and the physical layer doesn't succeed, then the router will go on the secondary failure. This example, I know I express it quite fast, but is an example that shows why you need two-layer protections. Because there are failures that can be solved by the physical layer and failures that cannot be solved by the physical layer. For example, the failure of this node cannot be solved by the physical layer, can only be solved by the logical layer. Sorry, I'm going a bit fast again we only have 10 minutes and I would like to give, so I'm skipping these last slides. I want to use the last 10 minutes to talk about research topics which are arising nowadays in this field. And again, as I said at the beginning of the class, I think it's a very healthy topic. There's a lot of research going on because reliability in the future smart cities, in the future services, is so important, right? I guess everybody knows 5G here. Everybody knows that one of the main message, one of the main service in 5G is the URLLC, right? The URLLC service type. which stands for ultra reliable, low latency connectivity. So obviously, if we really want to implement these services, we need protection techniques that can provide this very high level of protection, okay? So a first topic is, for me, this protection for future smart cities and protection for 5G, which is really the protection in the metro part of the network. On this topic, I have a project in my affiliation at UC Davis with Japan, and ICT is a Japanese institution. And here we are looking at this problem. Let me directly go to the point since we don't have much time. Today, the metro network is composed this way. You have leaves, which are basically the users and the base stations, the fixed users, which are these elements, and the base stations. The leaves of the network are connected typically through a tree-based architecture to the ring-based architecture in the metro, which is becoming more meshed even today, especially in the higher hierarchy. So this network has been traditionally just a collector of traffic. It was not an intelligent, reconfigurable, data center-enabled network. It was just a collector of traffic, and the traffic was going to the leaves, to the data centers located in the core of the network. Nowadays, there are some very clear technical directions. One technical direction is what people call edge computing. So some of the intelligence in these data centers is now being pushed into the metro network. And this obviously has an impact on protection. How do you do protection if now some of the services are no more in the core, but they go in the metro network? Second evolutionary trend, the control plane is becoming more dynamic. Now we have SDN, software-defined network. SDN allows the network to be reconfigured quickly. So how does protection takes advantage of SDN? And also requires a control plane which is reliable, because in SDN, you really need to collect the information. So not only the data plane, but also the control plane needs to be protected. Finally, there is a third evolutionary technological trend in metro, which I guess most of you know, which is slicing. Now, slicing means that the physical capacity of the network is carved into different logical slices or virtual networks. And again, how does protection evolves to take into account that in future operators will slice their network, okay? So here we investigated several directions of research for protection in metro. I just touched upon them. For example, we were having some publications and research on how to provide an SDN control which is disaster resilient. So most of our research is really focused not on small failures, but on large failures, disasters, as in this case, which cover several elements of the network. How you use machine learning. Now everybody talks about machine learning, right? So how you use machine learning to perform protection. How the concept evolves now that you have the data center in core, from network connectivity to what we call content connectivity. It doesn't matter that the network is connected as long as you can achieve a replica of your data in a data center which is close to you. You might be disconnected from the network, but connected to one data center where you have your service. So this is what we call the content connectivity. We also talk about some multicast, and we talk about using track recovery tracks, sorry, for protection. Let me give a little observation on this point. I don't know, but you might be aware that when there is a large disaster, operators have available movable network equipment. For example, movable satellite interconnections or movable base stations, such that they can provide, they say, relief. They provide coverage to people in affected zones where basically the normal network is broken. So now here there are research problems, right? How do you schedule if you have a network with several elements which are broken? How do you schedule? Imagine this network with all these elements which are broken, and you have a deposit in which you have all your recovery tracks, and maybe they are helicopters and drones, etc., etc. How do you schedule them in order to provide relief? So this is a very high-level description of these research problems. I also had several slides on protections against disasters, but we have only 3 minutes left. So maybe we want to take some questions and have any kind of curiosity from your side instead of covering additional material. So thank you for your attention, and please, if you have any questions, we can use these last minutes.
Yes, participants, your questions. Yes, questions from the participants.
So I see that there are some questions in the chat. I thank everybody for the congratulations. I've seen several people in the audience congratulating. Thanks a lot. Gerard is saying, what kind of tool is used for optical networking? I guess you are referring to tools for the solving of this problem. And usually the tools come from operational research. So there are tools from integer linear programming, which is basically optimization, solving big optimization problems, or tools coming from simulation. I guess there are platforms that you guys might know, like NS2, NS3, Network Simulator 2, Network Simulator 3, or there is a nice tool that I suggest everybody to check, which is called Net2Plane, which is from a provided by a Spanish institution. Pablo Pavón Mariño is the guy. Net2Plane. And it can be used to solve this kind of problems of optimization problems. I see another question, which is dedicated and how you find the capacity of the link. Yeah, it's probably a different way of using terminology here between me and Vasundhara. But the concept is dedicated simply means, simply means that if you have two connections, their backup paths, when they share the same optical fiber, they will take two different wavelengths, okay? So they say they have a dedicated backup capacity. They don't share the backup capacity, it's dedicated. In optical, for these problems, going to the second part of your question, the capacity of the link, this capacity is given, okay? So these arrows are associated with a given capacity, which can be, for example, 100 gigabit per second or 40 gigabit per second. So in our problems, the capacity is a given. Maybe you, sir, are in a different domain where the capacity is more of a outcome of your problem. But for this kind of problems, the capacity of the link is a given.